This is the second lecture of the morning session, and I'm very happy to request Eitan Sayag from the Ben Gurion University of the Negev, and he's going to. His title is Counting Lattice Points and Spherical Spaces.
Thank you very much for the introduction. It's a great honor and a great pleasure for me to be here. Can you hear me? Okay. At least one part is solved. I will speak about a certain problem which involves geometry, analysis, and somewhat number theory. And I will try to illustrate the ideas that, and somehow the motivation for us to study the problem. The basic thing is motivated by classical problems of counting lattice points in various compact sets in homogeneous spaces. And this is a very classical subject. Maybe I will formulate the setup and then introduce some of the ideas which played a role in our study. This is a report on a joint work with Bernhard Krötz and Henrik Schlichtkrull was giving a course here. Bernhard is going to come next week, as far as I understand. Is this visible? Okay. And parts of this project were also joined with Friedrich. No? The paper itself I'm going to report on is Friedrich is not the co-author, but it was a series of works. So what is the setup? Let me start with setup for counting. So what do we want to count? So in principle, we think about G, which is some kind of a Lie group, and on a space on which G acts, Z. And for simplicity, we assume that the action is transitive. So usually smart people work with a group acting on a space. More pedestrian people would, in a transitive case, would write Z as a G mod H, where H is some closed subgroup. Okay? But this is the general setup, and our aim is to count points in Z. So what does it mean to count points in Z? We will have a balance between a countable object, which is manifested by a lattice in G. Okay, so D in Z is going to be a countable diamonds. Okay, so if you want some kind of things you want to collect, so a typical setup for that would be gamma in G is a lattice, a discrete subgroup, and D is, say, the orbit of one point in Z. Z naught for me represents the class of H, or the identity element in G gives me a particular base point in Z. Okay? So this is the diamond I want to collect. But then, of course, they are infinite. So I need some compact sets in which these diamonds are organized. So I need a I don't know if it's visible here. I'll try here. It's visible. So in this setup, it's visible to you. Ares doesn't pay attention anyway, but let's see. So we have this countable sets, and the third item in this in this scenario is a collection which I parameterize by some real positive number, a collection of compact subsets. Of Z. Okay? So for convenience, I mean, you can think about the Euclidean space, and BR would be a ball of radius r centered at the origin, and gamma would be, in such a setup, the set we are interested in, so we want to count, the size of the intersections of D with this BR, or gamma acting on Z naught intersection of BR. So these are the numbers we are interested in. Okay, I don't know if this is visible. So maybe I will.
You're assuming it's a discrete set.
Let me. Yeah, the D is discrete set. Yes. So I don't really know whether this is which parts are visible and whether I'm writing too big. I don't know, but I'll erase the names. Try at least. So I introduce two quantities. So the counting problem requests a comparison between two quantities. The first one between, let's call it arithmetic quantity, which I will denote n sub r. So this n sub r is formally the size of the set of elements gamma in gamma mod gamma intersection H, with the property that when gamma acts on Z naught, this belongs to BR. So it's a simple exercise to see that the number I was mentioning over there is given by this formula. Okay? So this is the number of diamonds. Okay? And the volume of the ball, which I will denote by BR further on. Okay? Now these balls are not necessarily balls, and they're just compact sets at the moment. And the comment which was made ensures that these sets, these compact sets, intersect these discrete sets, finitely many elements. So the hope is that the limit of nr divided by br, where r goes to infinity, exists and is equal to 1. Okay? Nobody jumped volume with respect to what. Okay, we will put all these small iotas later, but it's kind of clear what's going on. We have this group G and H, which were erased from the blackboard. We will assume that, say, they are reductive or semi-simple, so we have measures, and the quotient space is unimodular, so we have a unique invariant measure, and properly normalized, we want to get this equal to 1. Okay? So I'll put all the small things later. I just want to. So this is called, if this holds, we say counting holds. Okay? So we are very happy. And we can ask for the further thing. So this is called sometimes main term counting. So this means that the number of diamonds is approximately the volume of the set where you're looking at. And now you can, of course, ask, next, ask for error terms.
You said this is a hope, you mean expect doing all of these inverse cases? Or
I will formulate the theorem. I will formulate the theorem saying that the hope is validated in this case. Okay? Just because you are impatient, if you take G to be SON1 to the power 3 and H to be the diagonally embedded subgroup, then in this space, this kind of triple product space, this property will hold for certain class of discrete subgroups gamma. Okay? So we'll sort out the parameters later. Okay, so the natural thing to do is to look at the difference, and properly normalized would be probably to divide it by the volume. So what we are asking is to estimate this difference. So the next hope, which might be simplistic, is to get this number less than or equal to some constant times the volume to the power minus s. So there's so many letters here. The error decays to 0, and the quantifier goes like that. There exists a positive constant c and a positive constant s, so that this inequality holds for every r. Okay? So there exists positive c and s, so that this holds for every r. Okay? So these are the kind of two questions one may ask. This is really a classical subject, and it really goes back to Gauss. So the mother of, so just example, I mean, I trust that 101% of my audience is familiar with this example, but nevertheless, so this is the mother of all these problems, these class of problems. And this goes back to Gauss. So in that case, Z is equal to R2, G is equal to R2, H is just 0. Okay? And the class of balls that we take are disks of radius R around origin. Okay? So in this case, maybe this should have been a better answer to Rami's question. In this case, so Gauss said there is a hope, so it's validated. Actually, Gauss proved more. He proved that NR divided by BR, now I normalize this, minus 1, is less than or equal than a constant times the inverse of R. Okay, and I leave this as an exercise to the interested audience. Okay? So people usually, there is an issue of normalization. People remember half, 1/4, never remember what we're talking about. The idea is that the circumference is the only enemy in this case, and only near the circumference we might have rational points. So the mistake is of the order of the length of the circumference. So the number of points in a ball of radius r is really r squared, or, well, there is a pi somewhere. Yeah? And the mistake would be approximately constant times r. But with these notations, it gets a bit ugly, but okay.
So in that language, S is 1/2, yes?
Yes, you are right. Thanks a lot. This is what I should have written. I just wrote from the memory. Yeah, okay.
That was good because you explained it was the boundary.
Well, okay. With every mistake comes a redemption. The point is that there is a famous conjecture for those who are searching for double star holds in this case with, and now I cannot remember, it's just going to be half of what I wrote, so 1/4. Is that correct?
3/4.
3/4? All right.
Plus epsilon or with lambda?
Yeah, so it does, and it's false with 3/4.
How
It's,
could
okay. So I wrote a minus s, you see.
minus s, so 1, so why is 3/4? 3/4 is larger than 1/2. 1/4, no?
Larger is more interesting.
Okay,
Yes, okay.
this is correct. I'm sorry. Okay, for every epsilon, there is a c epsilon such that the number of points in the ball, when you properly normalize.
Any other conjecture which is related to this?
I don't know. Yeah, so I exactly wanted to say that.
Just sits by itself.
I think this is what we want to say. Yes. So this is due to Gauss.
It's not related to either.
I'm not going to say anything about it. It's not related to as far as I understand, it's not related to any standard conjecture in automorphic forms or in number theory. It is just then, at the moment, isolated, as far as I know. Okay?
R should be to the power 1/2 probably.
Another mistake? Maybe. I will just believe you. No.
Like this,
No.
the mistake is
R. Let me write down. I just copy and that's it. Okay. I already eliminated the R square, so I cannot do this. Okay, so I'm sorry about this blunder. So this is, I'm not going to talk about that, but here is a remark which might reveal the kind of problems we are facing. Similar results to that of Gauss hold for families of convex sets, of other compact convex sets, as long as the boundary is nice, say C2 or something like that. So on the other hand, you can't improve on Gauss. You can't improve on what I've written here. Where is that? On this half, on Gauss, if you work with bricks, with squares. So if you're counting in sets which are kind of not so nice, then this is the error that you anticipate. You just check that. So we see that in this whole problem there is an issue of deciding which sets to count in. So this is one of the things I want to discuss. Before doing that, let me mention another famous example. Okay, just to be sure, I will not say anything new about Gauss circle problem. Okay, this is Gauss circle problem. Okay, but somehow I hope that now the target is clear. It's very elementary. We just want to count how many points there are, approximately, and then to say something about the error. And as I said, this is a very well-rehearsed subject, and many people have contributed, and I will not be able to mention all the names, but some names do stand up, and I will just mention them as part of my introduction. So maybe the second example, which is usually, I thought it's attributed to Selbergs, so this is due to Delsarte. So he initiated the study. I think he was a Bourbakist. I mean, people who here would tell me the history. He initiated the study, or he studied, I don't know if he initiated, studied the case of the hyperbolic plane, the upper half plane of Z being the upper half plane. So in this case, the groups which play a role are familiar to us. So G is SL2R, could be also PSL2. Just for simplicity. So this acts by fractional linear transformations on Z, and gamma, I will take it to be SL2Z. It's a different Z, sorry. Okay, so these are the kind of gammas we like. And BR is going to be a hyperbolic disk of radius R emanating from the point I. Okay? So the theorem of Delsarte is yes for star. Or in other words, counting holds. The number of points is indeed proportional to the volume of the ball. I should remark that there was a foundational work by Selbergs, later, Selbergs, who studied this problem. I don't know the history, but in relation to his trace formula. And he achieved fantastic results regarding this number NR. So Selbergs produced a certain asymptotic expansion. I'm not going to write it. Asymptotic expansion plus an error term. And the error term he got in my normalization is BR to the minus 1/3. And the asymptotic expansion depends on, so the quantities here are objects occurring in the theory of automorphic forms. So he used, maybe I'll just write the formula. I will not explain the notion in the formula, I'll just write it and you will feel what it is. Just, I'll copy it because I don't remember it by heart. I'm too old already for this. So, more or less, Selbergs' result, and I'm pretty sure that you will have many questions after that, and I will try to avoid answering because I don't want to take too much time of the lecture for that, but it's a beautiful result. So to formulate it, I will not use the notions I have introduced, but rather a different one, which is equivalent, but nevertheless. So I fix 2 points in the upper half plane and the hyperbolic plane, and define a number nr, but now with 2 parameters, z and w. And this number is going to be the numbers of gamma in gamma, gamma being SL2Z, which satisfies some strange inequality, twice the hyperbolic cosine of the distance between gamma z and w less than r. Okay? So just to fix ideas, the formula that Selbergs produced for this NRZW, I'm not writing the connection to these numbers, but it's very easy to work out. The formula is the following. It's square root of pi, and then a sum of some values of gamma functions I don't know if it is visible. And the sum goes over some eigenvalues between 1.5. hidden here is the main term, so it could be that I'm missing here s equals to 1. Ah, no, it's 1. Okay, the 1 is here. Okay. So the main term of this sum belongs to the eigenvalue which corresponds to 1. So in this normalization, these are eigenfunctions on L2 of SL2R divided by SL2Z of a certain operator, which I'm not introducing. Okay, so there is certain L2 theory which Selbergs produces, and today we call this a theory of automorphic forms. So it's a vast generalization of what he produced, and these numbers occur in a natural way in relation to exceptional eigenvalues and other things in this formula. So I just wrote this on the blackboard to say that this counting problem, it really relates to geometry, but if you want to really go further, you touch number theory. And in some sense, our study, which is not that deep at all, is trying to see how far we can go with analysis without getting into number theory. Okay? So in some sense, the shape of the balls, if they are allowed to be arbitrary, then in some sense there is no number theory. Okay? So if you can obtain general results in terms of the shape of the balls, then maybe your result is from geometric analysis. Okay, so I just wanted to give some feeling. I hope I didn't waste too much time on that. So just to finesse the setup, let me maybe formulate the result. Okay, so let me repeat. Gauss from the Math Olympiad, then Delsarte and Selbergs did this thing which is much more, can get much more advanced. And the next in this non-really historical setup story is the case of symmetric spaces. So for symmetric spaces, which is one way of generalizing the upper half plane, so okay, in this audience maybe I don't have to say too much about what I mean by symmetric spaces, but nevertheless, so I will take G to be a real reductive linear group, and I will assume that, so this for me is G is a subgroup, it's a closed subgroup of GLN-R or maybe GLN-C, and I want it to be invariant with respect to our beloved involution theta, the transpose inverse, and maybe a bar if needed. Okay, so some classical object of what we are working on. So in this setup, so it is known, but then G is unimodular. So there is a natural way to take a measure. And so the definition for symmetric space that I'm going to take, symmetric space, asymmetric space, is a gadget of the form G mod H, where H is the fixator of an involution on G. So tau from G to G is an involution. Okay? One can go with more general things. You don't have to take the entire fixator. You can take connected components. You can take something in between them. These are small things which are not relevant here. And they kind of vaguely broken into two classes. We have the Riemannian ones. Riemannian. I think I'm missing an N. Yeah. Riemannian symmetric spaces. So grosso modo, these corresponds to the case that H is compact. So if we define tau to be theta restricted to G. So theta was, maybe it was not clear, theta is an involution defined on this big group. I can restrict it to G and define an involution now on my G. And this leads to H, which is going to be, well, tau is compact, and it admits a Riemannian structure. So this is the natural. This is the natural generalization of the upper half plane. Yes, so if we take SL2R and divide, or maybe PSL, and divide by SL2, then we get our
What is the generalization?
G mod K.
G mod.
Okay? So we call it K now. Okay, so these are the G mod Ks. Okay? And then there is the non-Riemannian. Okay? So here the H is not compact. The involution is not conjugate to this restriction. But in both cases, the question that I want to address is what balls dr should we take? Okay, should is a hard problem. I want to take. Okay, so when I write here, it's visible, or?
Is there something like, for some natural, within some natural families, the balls give you the best testing power?
I don't know how to answer that. Okay? Yeah. But certainly I suspect that there is some natural class of balls, and I want to introduce them. Okay? So I will call these maybe geometric balls. Okay? So the geometric balls are obtained by, I will assume that as before. Actually, this can be done in a more general setup. So can be defined. I forgot to say that the spaces that we obtain here, is called G mod H, the symmetric spaces, are always affine. These are affine spaces. H is reductive, thus these spaces are affine. Okay, I will slowly go into more general spaces. Now, regarding the question whether the hope is validated, etc., yes, there was a foundational work on this by Duke-Rudnick-Sarnak and by Eskin-Mcmullen, and they established the counting property for all symmetric spaces. Okay, I will say more on that in a second, but they did not discuss, at least not in their paper, the error term estimates. Okay, and
The word affine, does it mean anything?
what?
The word affine.
To me, yes.
Over R?
Yes. Yes. Okay, so I'll go to a slightly more general setup. So this can be defined even for G mod H, where G is reductive and H is a closed subset. So closed subgroup. Okay, so I just wanted to illustrate the idea. So G has in it a maximal compact subgroup. Well, it has many, but and so G, being a reductive group, it carries with it this Riemannian symmetric space G mod K. This is a Riemannian symmetric space, which it comes for dinner even if it's not invited. So it has. So this guy has an invariant metric, and we can just lift it to G. So and then push to H. So that gives us a way to G mod H, and that gives us a way to construct balls. So let me just say this. So from G mod K, we lift to G. The distance between G1 and G2 is just this d G mod K of the cosets. And this allows us to define, well, I want to use the word ball, but with this kind of a ball in G. This would be defined as follows. BR with G upstairs, is the collections of G in G which satisfy that their distance from the unit is less than R. Okay? So, and now I want to use projections in order to get to the space Z. So these are K invariant and symmetric. Symmetric in the sense that for inversion, with respect to inversion. Okay? Maybe K invariant and BRG inverse is equal to BRG. This is what I meant. Okay? And now we want to put them. So I'm answering the question, what subsets in G mod H I want to study. Push them to G mod H. And the result is the following. I get a subset which is the image under P of this ball. And this is what I call natural or geometric balls. Geometric balls in Z. Okay. How much time did I use? I need to kind of organize.
35.
I have 35 minutes. Okay.
20.
I have 25 minutes? Okay. Thank you. Okay. So one property which is kind of nice and maybe convince you that that these are interesting balls is the following lemma, which is not difficult, but just I formulate it now. What happens when I perturb a ball? Namely, I look at a ball of slightly bigger radius. Then the statement is that if I act, so these guys belongs to Z, all these are Z objects, subset of Z. The statement is if I act by some epsilon ball in G on the R ball in Z, then I don't go too far. Okay? This is one nice property. And the second property, and I'm following these properties because these are essentially the only things we are going to use in our arguments. So whenever you are in a setup with these properties, you should be happy. There exists some positive C, so that B of R1, R2 is less than or equal than E to the power R1 times the volume of B of R2. Okay? And this is valid, well, almost for every R1 and R2. R1 is positive and R2 more equal than 1. Okay? Okay. And naturally, if you observe this construction, if you go back to G mod K, you will get the original balls that you had. So everything is consistent. Okay, so since my time is almost up, let me at least try to formulate some results. It will be difficult because I still have to introduce some notions. So I promised in my abstract that I want to discuss counting on certain class of spherical spaces. So the person from which I learned this notion is sitting in the audience, and the class is called wavefront spherical varieties. So this is due to Sakelaridis and Venkatesh, and earlier researchers introduced the notion of wavefront as a geometric property. So it will be not so trivial for me to give you a definition in less than 20 minutes, but I will try at least to give you the gist of what is it all about and to formulate the theorem. So,
Maybe you can give a non-example.
what?
Maybe you can give a non-example.
I already gave. The non-example. Yeah, I will do that. So first of all, the study of counting on symmetric spaces and beyond. This could be another title for the lecture. So, as I said, in the symmetric case, the symmetric case, I mean the following, yes? So G is a real reductive, as I said earlier. H is a symmetric subgroup. And gamma in G is a lattice, which formally means that it's a discrete subgroup, so that the volume of G mod gamma is less than infinity. Okay? Now, I will sequentially assume, I will assume that H is kind of nice with respect to the situation. So this means that gamma H, which is gamma intersection H, inside of H is also a lattice. This is a natural assumption. Turns out that this is the right setup to study things. And in fact, the volumes should be normalized. So volumes on G and H should be normalized so that the volume of H mod gamma H is equal to what? Probably to 1. I'm not so happy. So maybe this is correct. Maybe this is better. Okay? So this gives natural measure on Z, which, as I said, is unimodular anyway. And there were two groups working on this subject. The first is the Duke-Rudnick and Sarnak. And under these assumptions, they proved counting if gamma is co-compact. So if you further assume that not only the volume here is finite, but rather G mod gamma is compact, they've shown counting, and they sketched the idea how to do it in general. They never wrote it up because immediately when the preprint was out, and I'm kind of inventing the history, people here can tell me what really happened, Eskin-Mcmullen gave a different proof in complete generality using a different technique. So the technique of DRS was based on harmonic analysis. And in particular, okay, we'll say in particular on what. And the technique of Eskin-Mcmullen was based on something which is called the mixing lemma in Margulis's work, plus something that they felt they found out and gave a name. It's the wavefront lemma. So they indeed formulated it. I will say what it is in a second. And these two ingredients gave them a very general proof. So grosso modo, this is called the ergodic theoretic method. In these results, there were no error terms. Later, Neveu and Gauss and a different group of Iho and Benoit were refining this technique and produced some error terms without explicit value of this S that I have written, just ineffective error term. Okay? So the question remains, first of all, can one push the analytic method to get error terms? And can one go beyond symmetric spaces? So, question one, is it possible possible to use harmonic analysis to obtain error terms. Of course, when I write it, I feel it's a joke. What does it mean? Harmonic analysis was designed in order to produce error terms. When we're talking about Gauss circle problem, the first beating of the error term is based on Poisson summation formula. And the second question is, can we go beyond symmetric spaces? And the answers to these questions are sometimes. So I would hope to say that always we can just produce a complete general result, but we have partial results toward this, and I believe that actually this can be done in general. In a funny twist of events, our best result is obtained by adapting the Eskin-Mcmullen method. Namely, when we set up the approach to study the problem using harmonic analysis, we wanted to invoke some tools from harmonic analysis on spherical varieties, in particular on wavefront spherical varieties, which is a subclass. And we realized that we can actually prove a version of the wavefront lemma in that case. So finally, maybe theorem 1, which is not the best result that we have, but it's at least easy to formulate for wavefront spherical varieties. We have counting. Okay, so I will need to say something about this concept. And so so at the moment we need to make some assumptions, but I think that they can be removed. So the assumption on the lattice is that gamma is arithmetic and irreducible. The irreducibility is part of the game. It's in some way unavoidable. The arithmeticity, of course, is only a rank 1 issue. And in that case, I actually think that we can remove it, but I don't want to announce it. Okay? Okay, so, no, I apologize. We don't need that. I'm sorry, I got confused. No, we don't need that. Sorry, I apologize. For the counting itself, we don't need it. Okay, let me say something about spherical varieties and about spherical wavefront spherical varieties, and then I will formulate the second theorem. So, suppose that G is reductive, and H in G, I will assume is closed. So, closed. And reductive. And for safety, that people will not. Okay, that's okay. So I give kind of definitions. So I said the Z is spherical if the minimal parabolic of G, minimal parabolic P of G, have an open orbit on Z. This implies that it has finitely many orbits. And
Are these rational groups, real groups?
what? Real reductive groups.
That was a gamma, so
It's called real space.
Okay. Okay. So So this class contains the symmetric spaces and many examples occurring in Langland's program. So this was maybe most promoted by Skeleridis and Venkatesh, mostly by Yanis. In particular, the examples like G times H, where H is diagonally embedded, where G and H are classical. So I'm not saying any G and H will do, but for example, if you take GH to be GLN plus 1 GLN, then it will work. Okay? Okay, there are many more. I'm focusing now on reductive examples. Maybe some more example, which are more in line with Savin's lecture. So SO43 and a certain form of G2, which is denoted by G21. Okay, so this is as far as and then the example I said earlier, SON1 triple product with SON1 embedded. Okay, so here I don't mean this part. This is G, and this is H, and the space is G mod H. Okay. Okay. So I think I'm now almost ready to formulate the main result. Okay, so main result. And again, this name of wavefront will enter. I will say something about it in a second. So let Z be a wavefront spherical space. And I will make few assumptions. So, okay, first, without any assumption.
So what's the wavefront? What is the wavefront spherical?
Any symmetric is such. SON1 triple product is such. I can give you a list.
What is not?
Just give me the definition.
Okay? No, I haven't.
Okay.
You will be unhappy if I will give it to you. Okay? But I will describe it. Okay? I will describe the main property, which. So the main property geometrically is that so for symmetric space, you have an analog of the polar decomposition, KAK decomposition. For symmetric space, a similar decomposition exists. You can write G as H times A times K with a proper A. What you have to do is to take the two different decomposition of the Lie algebra, the K plus P decomposition and the H, K plus P and the H plus Q. And then you intersect the P and the Q and you take a maximal abelian subspace. This gives you an abelian subgroup. Okay? And this gives you a decomposition A, which is an analog of KAK. Just a second. This you followed. A wavefront space, spherical space, is a space for which such a polar decomposition exists. And this can be described in terms of its roots. So one can produce a list. Okay?
Why wavefront?
In a second.
Okay.
Okay? So the theorem. Main counting holds. So this you already seen. This was theorem 1. And second, assume further, and this is what I made a mistake, for the next, so this is the main counting. This means that the number of lattice points is correct. In order to get error term, we need further assumptions. So we need to assume that G is semi-simple and no compact factors. All these are kind of small technical things, otherwise the result is kind of not working. Gamma should be arithmetic and this I think we can probably eliminate, and irreducible. And finally, and this is our, at the moment, main burden, this has to be compact. And this is probably also possible to eliminate. Then there exists what I've written before. There exists a positive number which is completely explicit and ugly in terms of the parameter of the space Z and in terms of the properties of gamma, and I will elaborate on that in a second, such that the error is less than or equal than a constant times the volume of the ball to the minus s. Now, what is that different than the ineffective result? From your perspective, it's the same, because I have not written a formula. It's ineffective. But this is a matter of trust, or going to the archive. We can write a formula for S which involves what we call the rank of the spherical space, which involves the dimension of the spaces involved, and in particular, a parameter which we denote pH gamma, and was studied by previous researchers. And this is actually the reason I'm mentioning, because it's a key to, or somehow, the beginning of the argument in some sense. So the approach to this result is through analysis of matrix coefficients. So analysis of generalized matrix coefficients of unitary irreducible representations of G, which are gamma automorphic. So this exponent pH gamma looks at the spherical unitary dual and considers of G, and consider within matrix coefficients which are related to H-distinguished automorphic forms. And you look at the exponent, the LP exponent, where these matrix coefficients belong to. Now, what am I talking about? So it all began with Roger, right? He's here. So the matrix coefficient of a unitary representation, if it's a non-trivial one, decay at infinity. And in some sense, the entire study began when we studied the following problem. So can I erase this? How much time do I have? 5 minutes. So I will just not give a proof of anything, but motivate our approach. So approach via the study of matrix coefficients of unitary representations of G, and I should say generalized matrix coefficients. So there are few things in the soup. Maybe the most important thing is decay of generalized matrix coefficients. So let me explain what am I talking about. So suppose we have a unitary representation pi, which is afforded on a unitary Hilbert space H pi, and suppose we take a linear functional which is H invariant. So I'm in the setup of this G and H, and V, say, a k-finite vector. Then one writes a function on G which descends to the space Z. The function is the standard one, so m v eta of G is equals to eta pi G, maybe G inverse of V. Okay, so this is a function on Z. And this function is really a smooth function. It is G smooth. So it means that it belongs to a space. Belongs to some function space on Z, and it belongs to the smooth vectors. So starting point of the whole story, starting point was we want to show that any function which belongs to LP of Z and is smooth, in fact, decays at infinity. So if one analyzes the DRS argument, or in fact any kind of harmonic analysis argument for the lattice counting problem, there is a beautiful double vibration formula, which essentially is what people in automorphic call unfolding, which allows you to calculate the number of lattice points in terms of H periods of automorphic forms. So instead of studying H periods of automorphic forms, one decomposes this further using the automorphic Plancherel formula into matrix coefficients. So one needs to study the decay of matrix coefficients. And then we prove the following theorem, which is completely abstract result about H and G. This is, say, reductive. Let's for simplicity, say algebraic. And this is closed. And then we ask ourselves, when is it true that LPZ infinity, this means the infinity means smooth vectors, and P here is more than 1, and more than equal to 1 less than infinity. When is this contained in functions on Z which decay at infinity? This is just a notation for functions that outside a certain compact set become less than epsilon. So you give the epsilon, I give the compact set. So we found out that this happens if and only if H is reductive. So the DRS argument can run in some way only if you study reductive subgroups of G. So this actually gave us main term counting using analysis. As I explained, today we have a completely different proof which avoids any analysis based on this geometric idea. But if one wants to run the error term analysis, one needs to have an explicit way, explicit control on the decay. And for that, so since I have only 5 more minutes, and I wanted to mention this, so thank you, Siddhartha. I think this is the right time, I mean, I see no other good time, to mention that the key to the proof of this result was the paper by Joseph Bernstein, which Erez didn't mention, on the Plancherel formula. So I think if you will give me 1 more minute, I will just mention this result. It's a beautiful result, which I think deserves further audience. So key to the proof of the decay theorem, this theorem. So it has 2 sides. It's relevant for one of them. So it's relevant for the side that we thought we proved after we understand, and it took us a few years to understand that this was completely, it's not going to work, until we understood better what's happening in Bernstein's paper. So this is the notion of what's called weights, balls that you already seen, and Sobolev lemma, invariant Sobolev lemma. So all this is very simple. It's far from being in the list of the 10 best, but it's certainly a gem. So suppose that Z is a unimodular homogeneous space. And suppose, so first of all, we have a notion of a weight. So certain functions on Z, which are positive value, are called weights. I will say the definition because I don't have enough time. It has to be locally bounded, and it has to behave nicely with respect to the action of the group. Namely, I'll just say the second thing, with not the locally bounded. For every compact subset, if you compare omega of gz and omega z on that subset, the comparison is in favor. So, I mean, you don't ask for continuity here, so you need to ask something. So you want some comparison of this form, which holds at least in this compact. I made a mistake. It's compact set in G. But for every Z in Z. So this is called a weight. And there is a technology to produce weights. The technology is to take a ball in the group G and to act on a point, to look at the orbit of the ball on Z. So if this is G, you take a ball, which is just a symmetric, compact subset around 1, and you let it act on a point on Z. So in this way, you create interesting subsets. And if you take the volume, this gives you a function. So for every B, you create VB of Z, which is this volume. And the exercise is that this is a weight. And in fact, it's easy to see that if you take two different balls, the two weights you get are comparable in an obvious sense. You make a definition and it works. And then the lemma, with which I want to finish my lecture, is the following, and it's absolutely crucial for us. Suppose that you fix a P, which is between 1 and infinity, and you take K, which is bigger than the dimension of the group divided by P. Okay, so you fix a P because you are going to work with LP functions. Joseph worked with L2, but it's okay. Then there exists a constant C with the property that the point evaluation at every point is dominated by some constant times the volume of this ball to some power, which is minus 1 over P, times the LP Sobolev norm. So you need to take K derivatives restricted to this compact set BZ. Okay, so maybe it's difficult to appreciate this, but the idea is that in the regime of a group action, you can make the local Sobolev inequality sort of global. Because effectively here, you have an L infinity bound on a function. You have an L infinity bound of the function on Z in terms of its LP norm. And to finish, it turns out that to get this result, we need to have a converse to this inequality. And this is based on a recent work of Patrick Delorme and company on constant terms of tempered functions on spherical varieties. Okay, thank you very much for your patience.
Questions?
For that case, do you need an explicit decay rate of the matrix coefficient, meaning an effective decay rate of the matrix coefficient?
Yes, so in fact, such an inequality gives you such a decay because of the volume. So this is a general fact. You can prove this for any reductive homogeneous space. But on these spherical spaces, because they have kind of data, you can study them using linear algebra in some sense, you can calculate the volume of these balls in terms of the combinatorial information. You get some kind of a to the minus 2 rho, a corresponding rho. So this gives you a possibility to prove two things. First of all, that they are in some LP, which is not obvious at all. After they are in LP, we know by our general result that they have to decay. This already gives counting. But if you want to actually control how much they decay, you need to know that all of them are in the same LP in some sense. You need to have a P to put them all. And this is somehow the role of this guy. This is not an assumption because people have been able to prove that such an exponent exists for particular gammas, for some classes of gammas, in particular the ones I mentioned here. I'm hiding some other information that we are using, some bounds on multiplicities in the space of automorphic forms, etc. So all these things are really deep, but they are already known.
So your estimates for the error term, are they related to analytic continuation of some kind of zeta or something?
No, I think it's much less. I mean, it's not deep as that. It's not. We don't touch this nerve.
But is there expected that some kind of a metamorphic continuation is going to work eventually?
I do not know. It's beyond my competence.
Can you give us an example? I have one more question that you asked.
Can you give us an example of a non-wavefront spherical arrays?
Of course. This I learned from Yanis. But it's actually also, I mean, we have a different definition that they have, but it's probably the same.
It's SO32 mod GL5. Mod GL2?
It's real. This thing is real.
Yes. Yes.
Yes, also
Okay.
And GL2 is sitting as the Levy.
Yes.
So it's a reducible representation.
The question was, can I give an example?
Yes, but is it 5-dimensional irreducible representation or just?
These are two groups.
Yes, but
I'm just considering the homogeneous space, G modulo H.
no, you don't start with two groups. You start with a subgroup. Is there?
GL2 times SO1 or O1 is a Levy. And presumably that's the GL2. Any more questions? Okay, no, then let's start. Sorry.
Okay. Could you please briefly recall your definition of diamond and explain its relationship with your main theorem?
I think it's better I will answer you after the lecture, okay?
Okay, any more? If not, then let's. And we have lunch outside. Oh, and then